Unit 18, Banach-Stone theorem. Unit 18. Banach-Stone's theorem. Stone theorem. Banach-Stone theorem. Banach-Stone theorem. So contents, aims and objectives, introduction, maximal ideals in CX, and Banach-Stone theorem, closed ideals CX, summary, model question, aims and objectives. So here, introduction. Suppose X is a compact Hausdorff space. Let Cx be the set of all complex valued continuous function on X. Let mu be the set of all maximal ideals of C of X. Then we show that there is a one-one correspondence between the element of X and members of mu, which eventually turns out to be homomorphism. Homomorphism. Huh? So maximal ideals is Cx. Here maximal ideals Cx. So concepts, concepts. Huh? Concept means maximal ideal. Maximal ideal. Maximal ideal. So maximal ideal. Maximal ideal C of X. C of X. Here, let X be a compact Hausdorff space. Let X be a compact Hausdorff 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 complex Hausdorff space and Cx C of X Cx Cx with a set of all complex valued function with a set of all complex valued valued functions valued functions continuous functions on X continuous functions on X. So C of X equal to C of X equal to F such that if X2 Libra means pound symbol. X2 Libra is continuous. Is CTS means continuous. Is continuous. Is continuous. Is continuous. So we know that C of X is commute B star algebra. With identity defined by C of X. E of X equal to 1. E of identity E of X equal to 1. 1. We denote mu, the set of all maximal ideal is we denote by we denote by mu denoted by mu. The set of all maximal ideals. The set of all maximal ideal. Maxima ideal. Ideal. Maximal ideal. Maximal ideal. In C of X. In C of X. In C in C of X. Zero. 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 Banach stone theorem. Banach stone. Page number 307. Banach stone theorem. Zero. Banach stone theorem. Banach stone. Suppose X and Y are compact Hausdorff spaces. Statement. Suppose X and question formation is state and prove. State and prove Banach-Stone theorem. Now, sometimes they will give statement you have to identify. That is Banach-Stone theorem. Suppose the X and Y are compact Hausdorff space. Compact Hausdorff space. Compact Hausdorff space. Hausdorff space. Compact Hausdorff space. Then X and Y are homeomorphic. X and Y are homeomorphic. Homeomorphic. If and only if and only if C of X and C of Y means maximal ideals. C of X means maximal ideals in CF. Complex valued function. C of X and C of Y. C of Y is are isomorphic. Are isomorphic. 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 As Banach algebra. As Banach algebra. As Banach algebra. Proof. Suppose X and Y are homeomorphic. Suppose X and Y are X and Y are suppose X and Y are homeomorphic. 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 And X to Y is a homomorphism. And tau X to Y is a homeomorphism. 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 Define sigma. Define sigma. Sigma C of Y to C of X. Sigma C of Y to C of Y to C of X. C of Y to C of X by sigma of F by sigma of F equal to F circle tau. F circle tau. So here X to Y. X to Y. Then X to Libra. Libra means pound symbol. Libra. Y to F. To F. So this is the tau. This is the F circle tau. Is nothing but composite function. Then clearly sigma is homomorphism. Then clearly sigma is homomorphism. Sigma is homeomorphism. Morphism. Homeomorphism. Homeomorphism. Sigma F plus G. F plus G. That equal to F plus G circle tau. F plus G circle tau. Circle tau. That is what F circle tau plus G circle tau. F circle tau plus G circle tau. That equal to sigma of F. Sigma of F plus sigma of F plus sigma of G. Sigma of G. Sigma of G. Sigma of G. Sigma alpha of F plus alpha plus alpha of F. Circle tau. Circle tau. that equal to alpha F circle tau, F circle tau plus alpha sigma of F, alpha sigma of F. And sigma F into G, F into G, that equal to F into G circle tau, circle tau, that equal to F circle tau into G circle tau, that equal to sigma of F into sigma of G, sigma of F into sigma of G, sigma of G. Sigma of G. Now sigma of F sigma of G, that equal to F circle tau, that equal to G circle tau, G circle tau, that implies F equal to G circle tau circle tau inverse, tau inverse, that equal to G equation equal to G, that is equation number 1. And G belongs to C of X, G belongs to C of X, that equal to sigma of G circle tau inverse, tau inverse, that equal to G circle tau inverse, G circle tau inverse, circle tau, circle tau, that equal to G, that equal to G. Question number 2. Thus, sigma is 1, 1 and R2. Thus, sigma is 1, 1 to 1 and onto functions. Onto FNS means functions. 1, 1 functions. So hence sigma is isomorphism from. Hence sigma is a isomorphism from isomorphism from C of y, C of y and C of x and C of x and C of x. Hence, C of y and C of x. Suppose C of x and C of y are isomorphic. C of x and C of y, C of y are isomorphic, are isomorphic. Isomorphic and sigma C of x, sigma C of x to C of C of y is an isomorphism, is an isomorphism. Is an isomorphism. Is an isomorphism. Is an isomorphism. Let mu of x and mu of y, let mu of x and mu of y, mu of y be the maximal ideal, maximal ideal, ideal, maximal ideal of C of x and C of y, C of y, respectively, or yes, P and y means respectively, then by theorem. X is a homomorphic to mu of x. X is a homomorphic to mu of x. Homomorphic to homeomorphic to homeomorphic to mu of x. Mu of x. And y is a homomorphic to and y is a homeomorphic to morphic to homeomorphic to mu of y. Homeomorphic to mu of y. Hence, it is sufficient to show that. Hence, it is sufficient to show that sufficient to show that hence it is sufficient to show that mu of x and mu of y are homomorphic. Mu of x and mu of y are, y are homeomorphic. Homeomorphic. Homeomorphic to mu of y. To mu of y. Let x belong to capital X. Let x belongs to x. Let X belongs to X. Consider mu of X. Consider consider m of x. M of x equal to f belongs to c of x. F belongs to c of x such that f of x equal to 0. F of x equal to 0. This is like a kernel. Since sigma mu of x belongs to here m of x belongs to mu of x, mu of x. Mu of x, mu of x. Since sigma is an isomorphism, since sigma is an isomorphism, 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 isomorphism. So sigma of m of x, sigma of m of x, m of x equal to sigma of f, sigma of f such that f belongs to m of x, f belongs to m of x is a maximal ideal in Cy, is a maximal, is a maximal ideal, ideal in C of y, maximal ideal in C of y, maximal ideal in C of y, and hence, and hence sigma m of x, sigma m of x belongs to mu of y, belongs to sigma. So there exists y belongs to y. So there exists, there is small y belongs to capital Y, such that sigma m of x equal to y, sigma m of x equal to y. So we denote y by tau of x. We denote y by tau of x. Tau of x. Then the mapping, then the mapping then the mapping tau x to y. Tau x to y. To y. Defined by x x tau of x. Tau of x is a homomorphism. Is a homeomorphism. The homomorphism. The theorem is proved, hence proved. Hence proved. Most important theorem for 10 marks question. Right. Next. Closed ideals. Definition. 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 Let X be a compact Orthodox space. Let X be a compact. CPT means compact Hausdorff space. HAUS DORFM. DORFM. Hausdorff space. Hausdorff space. An ideal I in CX. An ideal. An ideal I in CX. CX is said to be closed ideal. Ideal. Closed ideal. PFX is said to be closed ideal if I is also closed subset of CX. Closed subset of closed subset of CX. We observe that zero ideal is ideal. We observe that we observe that we observe that zero ideal in CX. Zero ideal. Zero ideal in CX. CFX is a closed ideal. Using this definition, we prove one theorem. Right. Page number 309. 309. Suppose X is a compact Hausdorff space. Prove that or show that. Question formation. Theorem. Suppose X is a compact Hausdorff space. Suppose X is a compact Hausdorff space. Hausdorff space. Compact Hausdorff space. Let F be a non-empty closed subset of X. Let F be a non-empty subset of X. 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 Let I of M. I of M. F, F belongs to CFX. F belongs to C of X. F belongs to C of X. Such that F of X equal to 0. F of X equal to 0. 0. For all X belongs to F. Belongs to F. That equal to F belongs to C of X. F belongs to C of X. Such that F of F equal to 0. F of F is equal to 0. Then I of S is then I of F is then I of F is a closed ideal in CX. A closed ideal in C of X. In C of X. Closed ideal in C of X. Then means sometimes they will ask here, show that or prove that, prove that or show that. So proof. Proof of this theorem. Proof of this theorem. Clearly, I of S is an ideal. Clearly, I of F, I of F is an ideal in CX. Is an ideal in C of X. CX. Since first bit clearly F comma G belongs to I of M. I of M. M comma. So alpha comma beta belongs to found means Libra. That implies alpha F plus beta G belongs to I of F. Belongs to I of F. Second bit. Second bit. F belongs to I of F. G belongs to C of X. Okay. Heartbeat. Heartbeat. E belongs to I of X, where E is the identity element of C of X. E belongs to I of X, where E is the identity element. Identity element. Identity element of C of X. Of C of X. That is E of X equal to 1. That is E of X equal to 1 for all X belongs to X, means small x belongs to capital X. Further, 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 Fn subset IF, Fn subset I of M, I of M, Fn tends to F, Fn tends to F, Fn tends to F. That implies now Fn minus F tends to 0. Now Fn minus F tends to 0 as n tends to infinity. As n tends to infinity. As n tends to infinity. That implies, that implies. So now Fnx, now Fnx minus f of x, Fnx minus f of x less than or equal to, less than or equal to, now Fn minus f, f tends to 0 as n tends to infinity, n tends to infinity. That implies, it implies Fnx tends to f of x, Fnx tends to f of x for all small x belongs to capital X belongs to capital X. That implies f of x equal to 0, f of x equal to 0 for all x belongs to capital X belongs to capital X. Since Fnx tends to 0, Fnx tends to 0, tends to 0 for all x belongs to F, x belongs to F, and n equal to, so n equal to 1, 2, so on. So F belongs to I. That implies F belongs to I of F. I of F. I of F. So thus I of F is closed ideal in CX. Thus, thus, I of F, I of F, I of F is closed ideal in CX. Is closed ideal in CX. In CX. Is closed ideal in CX. Ideal in CX. We observe that I of X is, we observe that observe that I of X is the zero ideal. I of X is the zero ideal. Zero ideal. That is only element in I of X. That is only element in I of X is the zero function. Is the zero function. The zero function. Zero. This completes the proof, hence proof. So Stone-Banach theorem is for 10 marks. This is for 5 marks question. Sometimes they will ask for 10 marks also. So we'll prove one more theorem for 5 marks. Most important. Page number 310. Page number 310. Theorem. For short answer, 6 marks question. If X is a compact Hausdorff space, X is a compact Hausdorff space, Hausdorff space, Hausdorff space, then for any two non-empty, any non-empty don't find that. I just one of the closure subset F comma G subset closure subset F comma G F comma G of X. Then prove that question formation like that question. Then prove that or show that or show that I of F I of F that is equal to I of G that equal to F equal to G F equal to G. Proof. Oh, suppose F is not equal to G. Suppose SP means suppose F is not equal to G. Not equal to G. Then X belongs to G. X belongs to F. X belongs to F. That implies there exists. That implies there exists F belongs to C of X. F belongs to C of X such that F of X equal to 0. Such that F of X equal to 0. F of X is not equal to 0. And F of F is 0. And F of F equal to 0. That implies that implies that implies F belongs to IF. F belongs to IF and F belongs to I of G. Does not belongs to I of G. And F of X not equal to 0. Not equal to 0. Hence G subset F. Hence G is subset F. Hence, G is subset F. So if F is the family of non-empty, if F is the family of non-empty, 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 family of non-empty. Subset of X and Y. Subsets of X and Y. Set of X and Y. Is the family of closed ideals. The family of closed ideals. Closed ideals in C of X. In C of X. Then the above theorem says that then the above theorem above theorem says that map F to I of F, map F2 I of F to I of F. F2 I of F. From F into V is 1, 1. From F into V is 1, 1, 1, 1. We'll draw the map is Zanto also. Okay. Hence proof. That implies I of F equal to I of G. That's equal to F equal to G or G equal to F. Hence proof. This completes the proof. Hence proof. Okay. We finished in 9 units. Thank you very much. Wish you all the best. I'm leaving. All the best. Thank you very much.